was working on coming up with the theme for this webinar, I decided to go ahead and do a search for some common questions about using simulation during the injection molded part design. Just Google it and you get AI answers. There were so many that came up, but there were 5 that I felt were, I think, key questions that I've heard a lot, and questions that I had on my own way back when I started in the industry. So I felt that I would tackle those and show how SOLIDWORKS Plastics could help us answer all of these questions. So what they are, what I'll do, I'll go over the plastics matrix, give you guys a little bit of idea of the different levels of plastics that it's available, and then walk a little bit through briefly over the workflow, how easy the steps are, and then I'll actually show that as well. And then I will go into the questions on how do I prevent short shots, where's my best gate location, how can I reduce sink marks or voids, why is my part warping? That is probably one of the biggest questions. And then also a little bit about how accurate are my results. So I'll give some tidbits or tips on how to get more accurate results and things to think about when you're running a simulation. So first I'll cover the SOLIDWORKS Plastics matrix. So we're going to look at the available packages. There's Plastic Standard, Pro, and Premium. There's 3 levels, just like SOLIDWORKS comes in 3 levels. You can run any level of SOLIDWORKS Plastics on any level of SOLIDWORKS. It is an add-in in SOLIDWORKS, so it is a separate purchase outside of SOLIDWORKS. But it does require a SOLIDWORKS license to run SOLIDWORKS Plastics. Plastic Standard is just the filling phase of the injection molding process. So we have fill, pack, cool, and warp. The filling simulation is going to show us is how the material melt flows through your part cavity. So this is good for part designers. It's geared more towards guys that are just designing parts and want to see how the plastic is going to flow through their part, help identify weld lines and air traps, sink marks, and then also work with multiple gate locations. So if you have a large part, you can do more gates than just one. And so we can look at all of those and positioning those gates. So we'll look at some of that today in the software as well. And then professional includes the packing phase. So we go from fill to pack, but it also has tools that are geared more for guys that are doing mold design, working with multiple cavities. The runner balancing tool is really nice to use to be able to get equal pressure and fill times between your cavities. There's an insert and overmolding. So we can do 2-shot overmolding, or co-injection, bi-injection, insert molding. We can mold over a plastic, or we can mold over any of the metals that are in the library. Rubbers over plastic, that type of thing. We also have hot runner systems that we can do in professional, and also work with valve gating. So if you have a large part with a large manifold system with valve gates on there and you want to do valve gate timing so you have a smooth flow across the part, we can do this with professional too as well. And professional also has your fiber analysis stuff. So if you're using fiber filled materials, you can look at the fiber orientations in the part and actually even export out from the model into something like Digimat and go further into other FEA with the fiber orientations in our part. And I mentioned also co-injection and gas assist. So it's more of the oddball injection molding, not as popular stuff. I mean, single material is probably 98% of the industry right now. And then plastics premium, so that's our highest level. We get everything from standard and pro, but it includes the cooling analysis and also your warp analysis. So the advanced cooling is going to actually run a CFD analysis on your cooling channels, which I'll go pretty deep into that today. And then we'll also look at part warpage. So that's really one of the things I'm going to concentrate on the part that we're looking at, is that warp analysis. So let's look at the workflow. So we're going to start the process with a SOLIDWORKS part model. we'll start a new study. Then we just have to apply the material from a database. We have over 3,500 materials. That database is being updated regularly. Every service pack of SOLIDWORKS Plastics that comes out, we get more material updates. They'll remove old obsolete materials and add more advanced materials in there. Once we apply our material, then we actually choose any process settings. We add any boundaries. So our boundaries are like the injection locations, or this is where we can specify control valves, our clamp force direction, those type of things for boundary conditions, water inlets, all of those as well. The next step would be to mesh our part. So we have everything set up, we're meshing. I'll show a little bit about the mesh, but it's really robust and easy to use and fast in SOLIDWORKS Plastics. Then we run the analysis and then look at and analyze the results. So it's really pretty short process, especially when you get into the part modeling side and you're just looking at injection locations. You start a new study, apply a material, mesh the part after you set your injection location, and run the analysis. So it's pretty quick, just a few steps. So we'll start by looking at just this simple part. It is a fan bezel housing that goes inside of the GoBlend blender that one of our simulation guys created. There was a webinar yesterday actually talking about this too. So I'll start a new study. I'm going to use the solid mesh type. So there's two different mesh types, solid or surface. I'm going to choose solid because I have a bunch of ribs in there. And I'm going to choose a recently used material, a Macrolon, that I use a lot. We can see that I have my molded part cavity defined, and now I'm going to define an injection location. So we can do an injection location off of a face or a sketch point. I'll use a sketch point in this case. A lot of times I like to put a split line on my model that is the shape of my gate, and I can choose that. Next, I'll go ahead and mesh that. I wanted to show how pretty quick the meshing is. I'm going to do a coarse curvature-based mesh on this model and go ahead and click on the create. And it pops up with the mesh pretty fast, right? Now we're doing the solid mesh internal. So once it finishes the solid mesh, so it does a surface mesh and then a solid mesh, it's using a tetrahedral hybrid mesh. So this automatically gives us 5 layers of thickness through my mesh, which yields really good, accurate results. I don't have to go in and see what my wall thicknesses are and then make my global mesh density that and then refine the mesh. It's a really robust, easy mesh to do. So once we have it meshed, we're going to go ahead and run a fill analysis on this part. So what happens when we run a fill analysis, it's going to start the analysis manager. So this sits there and runs, and we can see things pop up on the screen, and it talks about what's going on in there. So instead of watching it run, I'll go ahead and we'll look at the result. So what happened on this part, we have this single gate placed on there. I get a short shot indication. So I can see in several places on my screen, it tells me a short shot's been detected. I have a warning right here that says a short shot, and I can see visually that, hey, it did not fill. So what do we do next, right? So I have that. How can I prevent short shots on my model? So I want to ensure that I have complete mold filling before I go further into my part design and all of that. So I want to look and see what can I work on in my model to get it where it does not short shot. So some of the things that we would look at, your incomplete fill may happen due to poor flow, freezing, or thin sections. So all of those kind of go hand in hand. When you run a thin section, it starts to solidify pretty quickly. So that actually reduces the flow in the part. So one of the things that I always look at, we look at wall thicknesses. It may be a case where the designer was trying to see how light he could make the part, and then he chooses a wall thickness that really that material will not flow through really well. If that material is what is specified, then we may have to change the wall thickness. We can compare polymer grades and find a material that may flow easier, or we can adjust wall thicknesses. So in this case, I'm going to choose to adjust my thicknesses. The other thing that I look at, we still see that I have, it says short shot. I'm looking at my pressure at the packing switch time, and I can see that I'm really high on my pressure. So my pressure limit I have set is at 100 megapascal, and I'm hitting that limit right here. So I know that it's having a lot of trouble filling this area out on my part. We can see here really high pressures in that area. So when I look at my wall thickness of my part, I see that the ribs inside and the outer flat part are pretty thin. So what I want to do is increase these a little bit to see if that improves my flow. So I can go into my model, and in SOLIDWORKS and plastics, since we're working inside of SOLIDWORKS, it's really nice to be able to, I can duplicate my study. So what this is doing is creating another configuration in my part, allows me to go in and modify my wall thickness. So if you're familiar with SOLIDWORKS configurations, if I make a change to one configuration of the model, I can leave the other ones untouched. So I'm not messing with this other study. I'm copying all of my settings, the material that I chose, my mesh settings, and all of that are getting copied over. Then all I need to do, once it finishes copying these things over, I can go in to my feature tree. We can see that I'm on a new one. I'll go over to my feature tree, and then I could actually come in and make modifications to any of the dimensions that I want. So I could come in and change the wall thicknesses in a certain area in my model, or also I could come down to my rib and make any changes to my rib in the area as well. So once I do that step, then I can go to Plastics Manager and remesh my model. It's going to capture those new settings, right? My new mesh is capturing the new geometry, and then I can run the simulation again. So instead of going through those steps, I have the results of the simulation. So we can look at my fill time plot on this one, and we see that I get a full fill. I'm not showing a short shot anymore. You can play the animation and see how the part is filling. I may not like having this gate here. We can look at gate locations here in a little bit. I wanted to make sure that I have a good fill with that gate choice, but we can see I also have a pretty strong weld line in this area. So this could be a weak point in the model. If we're going over a fan motor, a fan blade, there's a lot of heat that gets pulled through there that may cause some degradation of the part, and that may be a weak point in my part. So I think maybe we should look at gate locations. So our next step, where's my best gate location? So we're going to look at gate optimization with the filling analysis. So our animation on the left is the one that we just finished, and the animation on the right is if I move if I move the gate to the center, I can also add additional gate locations around there. So we could consider this a direct sprue down to this area, and the sprue and gate can be clipped off around the round hole. And we can notice that we have a more balanced fill, right? We're filling out all the way to the edges at the same time. So our gate position affects our flow patterns, weld lines, and pressure. Our fill simulation is going to show how the plastic advances with each gate option. So we'll look at this as well. We can see that I have our fill time is equal on all four corners, right? And we're filling pretty equally. And my pressure in the fill, I have a lower pressure than we did on the other one because I have additional gates. And we also see that the pressure on these edges is pretty equal as well. things I can look at on the packing side, right? I can look at my volumetric or my sink marks at ejection or one thing. That's looking at our wall thicknesses. So we have these additional gates in there. I can look at my sink marks as well on that. So now that I saw, okay, I have sink marks, how can I avoid these, right? So what do I do to reduce my sink marks? Preventing surface defects in thick sections. So one of the things I look at, we saw the sink mark. Another thing that I look at is this isn't a result that's in the packing simulation, and it is part of Plastics Professional, right? So we have the packing phase and Plastics Professional. When I talked about the how to reduce sink marks and voids, I mentioned voids. So we can't really see voids in the simulation, but what we do is identify areas where a void could occur. So looking at your volumetric shrinkage during the packing phase. So what happens if we're injecting into a thick wall section in the mold? As soon as the plastic hits the mold walls, it starts to solidify. So it gets more and more solid as we go through, especially in the packing phase, but we may still be liquid inside that thick wall section. So what's going to happen is that thick wall section being solidified, it's either going to get pulled in, creating sink marks, or if it's solidified enough, the polymers inside that kind of just rip themselves apart, the molecules in there, and form all these tiny voids and bubbles. So that's how a void could occur. So I look at my volumetric shrinkage in end of packing. In this case, I have my clipping plane on, my ISO clipping plane, and I can adjust the lower region to adjust what I'm seeing visually. So this is showing me the highest area shrinkage. What I want to do is make adjustments to my model to reduce this volumetric shrinkage, right? I want it more equalized throughout the part. So what I did on this part, I made another modification to make the center boss that's in there, that really thick wall section, more uniform with the rest of the wall thickness of the part. So now I've adjusted my volumetric shrinkage very close to the same rates, but we see now my shrinkage overall of the part is more equalized, right? So more balanced through the whole part. This is definitely going to help on that side of it, and will also help our sink mark at the same time. All right. So why is my part warping? This is the one that I think I get a lot of questions on. It's really pretty simple to answer. So we're going to look at controlling our part warpage with our part design and also with any process settings. There's some really nice tools within SOLIDWORKS Plastics Premium for working with the warpage. First, I want to look at my part design, right? If I'm looking at this part, this is the one that we just finished filling, right? So I have my uniform walls. And what I want to do is look at my warp result. In this case, we can see I have a total deformation plot. My goal is to make this plate as flat as I can because it has to bolt together, and I don't want it stressing the part out. I want to have it as flat as I can get it. So looking at this part that we just ran, I can take my total deformation plot, turn it in the Y direction, right? So my compass down here in Y direction. So what I'm looking for is how it is bowing in the Y direction. So how flat is it? I've got my deformation scale bumped up to 10. So this allows me to see how much I mean, exaggerates how much it's smiling. I guess I can call this one smiling. And we can see that the maximum is 0.340 millimeters. So we're going to try to reduce that as much as we can with our part design. So this is the case with the non-uniform wall. So what happens if we go in and look at our part cooling time? So our cooling time is the time it takes the part to cool from the packing phase till the ejection temperature. So this is the longest part of your cycle of the injection molding process. So this is where you really want to make sure this is uniform. It's also how you can kind of control the cost of your part. If you can get your cooling time shorter and more uniform, you're going to have a better quality, but you're also going to have a shorter cycle time because that's the longest process. So that's one thing to look at on the part design side is we can look internally at our cooling times. Because I chose to use a solid mesh, I can actually measure inside on my part and look at different areas of my part. And we see this is that thick wall section. I haven't thinned it down yet. And we can see there's like 1.38 second difference in cooling time in there. So that is also non-uniform cooling, which non-uniform cooling is the leading cause of warpage. So let's modify our part, make the thickness more uniform. I rerun the analysis. I have my deformation scale, my Y direction, and we can see it's flattened out even more. So this is allowing me to, it's almost cut it, well, more than half, 0.1087. It's cut it down that much. So a uniform wall gives us more uniform cooling. I can look at my cooling. Now there's only 0.470 seconds. We can see that I've thinned that wall out to make it more uniform with the rest of my part. This is what I did with the volumetric shrinkage and the sink mark as well. It gets, those are a lot better. So now I'm a more uniform part, more uniform cooling. Pretty happy with the result I've got there. So this is showing us that our uniform cooling leads to uniform shrinkage in the part and also reducing our warpage. So this is the other tool that I like to work with inside of SOLIDWORKS Plastics. Now that I've got this set, and we know that injection mold temperatures can be controlled with our cooling channels, right? But I don't have a channel layout or anything done yet in this case, but we have a boundary condition called mold wall temperature. So I can apply that boundary condition to my entire face on one side of the mold. And we look at our settings. So my mold temperature is set to 100 degrees. So it's assuming that I have a uniform mold wall temperature of 100. If I go into mold wall temperature and pick this face, I can actually increase the temperature on that face to 103 degrees. This will actually allow me to go in and look at my warp and what does that difference in temperature do to my warpage. So I'll look at the Y direction again, and now I can see I'm at 0.066. So I even cut it down even more. So that's pretty impressive to be able to do that. I'll change my deformation scale to 10, and then we can zoom in at this. So we've turned that smile, we've flattened it out more. So it tends to, warpage will tend to follow where the heat is in the mold. So if we think about that, maintaining your process settings in the mold is going to actually help you look at that. But utilizing this tool of the mold wall temperature gives me a good idea of what effect temperature will have on my warpage. So pretty happy with my design right now. And we can look at, where did it go? I just did that, didn't I? Yep. Okay. So now we get to the point how accurate are my results? Trusting accuracy in simulation. It's true with any simulation package. People are asking how accurate are your results. You hear a lot of garbage in, garbage out type stuff, but the package in SOLIDWORKS, there's a lot of tools and it's set up to help you succeed. So the mesher works really well. As we saw, it auto refines areas. We don't have a whole lot of mesh things that we need to change, but we can. The polymer database in SOLIDWORKS Plastics, in 2019, I believe they started working on revamping the database. They added specific heat curves, thermal conductivity curves, but working with major manufacturers around the world, getting the most up-to-date data. So your viscosity data, PVT data are very important in a analysis. So Covestro is one, this macro one that I chose. Our data source, if we look down here at the bottom, it shows my data source came from Covestro. So this is test data directly from them that the SOLIDWORKS R&D department takes their test data, creates the material and tests it, and then we get a good, accurate material out of it. Really nice to have those things. If your material is not in the database, you can use the user-defined database and define your own material, but you need to get proper material data from either the manufacturer or sending it out to a testing lab and have it tested. Then you can go in and enter the material into the database. So what we look at for accuracy, it depends on our material data. Process settings is another thing we can look at. So as a part designer, you may not know what all the process settings are in a machine. By default, our mold temperature and our melt temperature are set based on the material that I chose. So in this case, if we look at this material, there's a recommended melt temp of 300 C and a recommended mold temperature of 100 C. Remember that temperature is what we had set in our setting, and then I went in and made the mold wall temperature 103 below it. But you have min and max temperatures and things like that that are given here too as recommendations that will allow you to go in and make any adjustments that we want to it. So that's another thing. The process settings. So if you're trying to optimize an existing cycle on the shop floor, you can actually get the setup data for your flow rates, your pack rates, your material, the fluid flows and temperatures and all of those things to get the most accurate. So if you have an existing process and you can enter all of this process data, we can go as deep as actually using screw diameters and screw positions, which most of the modern injection molding machines now, that's how you set your shot sizes and things like that based on the screw diameter and the positions, and then your screw speed for your injection. So instead of just using a specific pressure, we can do that. And we can also do profiles. So you can get really deep into the process as well. And the other options that we have with quality, your mesh quality is one of them. So getting a good mesh quality, it's easy to do with plastics. There's some tools you can go in and edit if you have some elements that are not very good, but it'll identify intersections and things like that that we can correct. By default, the default settings for the mesh, it works off of the global average part thickness. So I remember I was talking about that when I talked about the mesh type, but it will create that for us by default and get a really robust. But we have the ability to actually increase our mesh, have a more dense mesh than the coarse mesh, and still have the curvature refinement. So we want to make sure your mesh captures all of your geometry well. You don't want radius to show up as chamfers, right? So we want to try to capture the geometry as best we can, especially in thin wall sections around our injection location, those type of things. So we want to make sure that those have our best mesh. So one of the first things that I think about when I'm looking at thinking about accuracy, when we're focusing on part warpage, we really want to consider running a cooling analysis, right? Because one of the things that I talked about was that setting, right? Our mold temperature setting of 100 C. Well, it is calculating 100 C as you have a completely uniform mold. We know in the injection molding industry, you're not going to have a completely uniform mold temperature. It may be pretty stable, but it's not going to be uniform all around the part. So we want to be able to look at our cooling analysis, identify the hot spots in the mold, and also really mimic what's going to happen in the real world. So our warpage that we saw, and we added the mold wall temperature, that was probably the absolute best case of what you could do. But you really need to try to go in there when you're looking at that and work on cooling channels. That is why the advanced cooling analysis is part of premium to go with the warpage analysis, because we want you to run that. So it's beneficial to run the cooling channel layout and then also assign a virtual mold so we can see the full mold cooling effects. We don't have to model in a mold cavity or any of those things. We have the virtual mold, so it's going to surround our part. We define the virtual mold with the material that it's made out of. The material library has P20 and H13, A2, beryllium, copper, all of these things, major mold materials that are out there. So we have the ability to do that too. And then we can choose our coolant inputs as well. So we can use this to validate a mold design prior to approving a mold design. If you have someone else building your mold and design the mold, they send you the mold design, you want to look at the cooling channel layouts and make sure that you're getting a uniform cooling on your part. And we can also use this to verify if you have an existing mold that you're having quality problems or mold or defects and things like that. You can use that cooling layout and say, okay, this is what we're getting. Maybe I want to try a different type of cooling channel. What happens if I add bubblers or another cooling channel? Can I improve that process? So let's look at how we can define our cooling channels, right? So really nice tool. We do not have to have solid models of our cooling channels. I want to make sure and edit my simulation to cooling simulation. So we have cool, fill, pack, and warp as part of premium. I still have my macro on, but we now see that I have cold runner system, cooling channel, virtual mold as my options. So cooling channels, the way we define these, we can use sketch lines. We don't have to have them solid modeled. So I'll go ahead and select these and show them. And we can see that all we're doing is selecting sketch lines. I'll come in and edit a definition so we can see. We select a sketch line and we specify the channel parameters. Is it a general? Is it a bubble or baffle? And then whatever diameter that is. So we have the ability to go in there and define those really quickly. I could box select all the channels if they're all the same size and apply it to that. Then the next step is our virtual mold. So this is basically just surrounding all of your cooling channels in your runner system. Then we assign our material steel. The cold runner system works very similar to the cooling channels. So I select a sketch line and my runner legs, tell it what diameters those are, what shape I want them, and then I can mimic a runner as well. So what I'm doing here is excluding my runner from warp, because typically when you eject the part from the mold, you don't want your runner in there. So this is going to give you more accurate warp results. So it actually excludes that from the warp analysis. Then what we do with our cooling channels, we actually pick our inlets and outlets, we set our flow rate, and we set our temperature that we have on that side of the mold. So we can actually specify A side or B side, and we can change the temperatures in different areas depending on what we see with our results. Then we go in and mesh our model. So meshing the model, it's going to capture all of the cooling channels and everything. I'm going to go ahead and switch over to the results that we've seen on this one. So I've got this cooling system set up, and we can look at our part cooling time, 5.69, a little less than it was. We still see a higher area of part cooling around our runner system up there at the top. And if I look at my cycle average mold temperature, this is going to let me look and see basically what the mold wall temperatures are. And I can see I have a hot spot up inside the part. I can use my evaluate tool and measure this. We're seeing like 124 degrees in a certain area, 130 in other areas. So it's pretty hot. What do I need to do in this case? So I can come in and add more cooling, right? That's one thing that I could do. I can see the pressure of my coolant system, so we can look for pressure drop. We want to make sure that we have velocity as well, so I can look at the velocities. Notice the blue lines around the edges. These are like the drill points that are really kind of dead areas, but fluid still kind of flows through there. Because it's a CFD analysis, it actually does the cooling on that part of the mold as well. We can look at the warp, and then I can look at my warp in the Y direction. I'm concentrating on that. So we have a 0.147. We're kind of back to almost where we were before we ran a cooling analysis. So that perfect mold temperature is kind of gone away, right? So we have non-uniform cooling due to our cooling channels. So what I did in this case, go in and I modify my cooling circuits. So I have additional sketch lines in the model, and then all I have to do is add those sketch lines, remove another one, and then also I want to add a bubbler down at the bottom. So we're going to add a bubbler. I do this also with sketch lines. So I don't have to model in a bubble tube, or if I have a baffle, I don't have to model that in. It happens during the meshing process. So I split my my upper and my lower lines. So instead of flowing around the full thing and getting hotter as it goes through, right? I want to flow straight through, have more lines. I have more uniform cooling in my circuits. So I did this on both the top and the bottom. So some things to think about. I talked about using sketches versus solid. We can create solid models of your cooling channels. The advantage of using the sketch-based cooling channels, the mesh type that Plastics places on the cooling channels is better for running a CFD analysis. It solves faster. It reduces the amount of elements in your model versus the tetrahedral hybrid type of method, because that's what I would try to apply to it. You get a better, more uniform, round mesh by using this. So also with the bubble tubes and baffles, they're defined from a sketch. We don't have to model that in. And we can see this is a section view of the mesh through my bubble tube. So the fluid would flow through this way, go up the center out here, and then cascade down and then back out this tube here. So it models that all in the mesh automatically for me. I don't have to create a solid model of that, which would take a lot of time. If I'm working on a part design and I want to see how that works, just having sketch lines, this is just 3 sketch line segments. I have one segment for that, one segment for my bubbler, and one segment exiting. Very simple to do. I don't have to have a full model. So after I do that and then I run my analysis, then I can look at my cooling or my cycle average mold temperature again after I run the analysis. So in this case, I have my virtual mold shown in sections, so I can actually look at the temperatures above and below my mold wall temperature in that area. And remember when we were working on our warpage, we had 100 degrees on the top, 103 on the bottom. Well, I hit that pretty darn close. In this case, I'm 3 degrees different, 99 on the top, 102.7 on the bottom. It changes as we go through. There's some, I could probably find nodes in there that were exact. I can see though that I have a more uniform temperature color all through my part. Might be a little colder up here in the top, but remember this is where that thick wall section is, where the rib and the boss is. So it may be beneficial to be a little bit cooler up in this section there. We want that to start solidifying quicker. And since I was looking for my flatness, one of our other tools that we have is we can actually do XY plots of my deformation. So I have my total deformation in my Y direction, and I turn on my XY plots, and I can see I've got basically around the corners and the centers of this part, I have 8 points shown. So what this is going to do is show me the displacement of each of those points. And I can look at my plot. We see it looks like it's going up and down a lot, but I can find my highest and my lowest. There's only 0.053 millimeters difference between that. That's only 0.002 of an inch. So that is pretty flat. Remember when we started this, we were probably closer to almost 10,000. So reducing our wall thickness, making it more uniform, working with our cooling channels, all of those things to get an accurate result. I think if we think of the word that actually works the best is uniform, right? You want uniform cooling, you want uniform wall thicknesses, uniform pressures, uniform fill time. All of those things go together to make a really good plastic part. You're going to get better quality parts by doing all of this with the simulation, looking at your design, and you're not having to really try to process out like adding pack pressure to reduce your volumetric shrinkage or reduce your sink marks, those type of things. So